Hey guys, welcome to lecture number 8, I think. Well, you, we will talk about linear algebra today. We will start, we'll start with something, easier. Well, I want to say very easy, but something easier with matrices of order 2 and 3. Okay, let's get started. And then next week I will do matrices of order n. But anyway, the picture is very similar. And in fact, oh my, lecture number 8. So let's do it here. Let me write it. Lecture 8, matrices of size 2 and 3. Okay, that's it. Okay, now, so matrices of order 2 and 3. I think I'm going to do the whole picture. I will even talk about the eigenvalues and stuff like that. Let's start. So let's start with, first of all, I'd like to start with matrices of order 2. All right, so we know that a matrix of order 2 looks like this. So A is in M2 of C. You can put there any field you want. You can put real entries and so on. It doesn't really matter. And this matrix would look like this. So we'll have the entries. So I'm just going to say A, B, C, D, where these guys A, B, C, D are real, complex numbers, right? Like I said, it can be real. It doesn't really matter that much. And the first thing that you need to know here is, well, you know how to compute A squared and everything like that. There are some things that we need to know here. And the two things are the trace of A, which is the sum of the elements on the main diagonal, which is in our case is A plus Z. And another thing is that the determinant of A is AD minus BC. So this is the trace and this is the determinant. Now, there is one thing that you need to know is that the Kaylee Hamilton equality, which says the following, is that A squared minus trace of A times A plus the determinant of A times the identity, this is the null matrix, right? Where the identity, let me remind you, is this matrix, 1, 0, 0, 1, and the null matrix, O2, is this matrix with the entries, all of them are zeros. So any way you put it, anything you do, if you have a square matrix of size 2, this equality holds true. Always. So you will always have this equality. So this is the Kaylee Hamilton. Well, it can be proven directly. If you want, you can prove it directly just by computations. Like you write the matrix A, B, C, D, you square it, and you keep going, and then you'll see. Anyway, I'm not gonna dwell too much on the proof of this equality. You take it for granted. So Keep this in mind, though. This is one of the most important things for matrices of order 2. And you will see that when we will talk about the eigenvalues, it will give you some information. So these two guys here, the trace and the determinant, will give you some information. The eigenvalues are related to these two quantities. From Kaylee Hamilton, one can infer, so as a consequence, let's say, of Kaylee Hamilton, well, this is just a matter of computation, is the following. So for example, if we have like an invertible matrix, so if A and M2 of C is invertible, so when I say it's invertible, I mean that the determinant is non-zero. We can always compute the inverse, and well, those of you who have taken a linear algebra course, you know how to compute this. There are plenty of ways to do it, using elementary transformations or using the adjugate of a matrix and so on. Then we have this equality, so we can express the inverse in the following way for 2 by 2 matrices, and this will be, just like I said, it will be 1 over determinant of A. And this quantity here, and I would like to write it in this way, is nothing else than just the trace of A times the identity minus A. This quantity here, you will see that this is nothing else than just what we will call the adjugate of a matrix. And for 2 by 2 matrices, it can be computed in this way. And anyway, and you will see. And moreover, we also can prove that, and the trace of A inverse, well, you will see that we can compute this using the eigenvalues, but the trace of inverse will be nothing else than just the trace of A over the determinant of A. So these are consequences of the Cayley-Hamilton equality. This is, anyway, you don't have to know this by heart, but you can derive them easily, right? You just, for example, you can multiply by the inverse, right? The Cayley-Hamilton, and you will derive exactly this. So there is no problem. And also, once you derive this equality, you just take the trace, and everything is there, right? So the second relation follows from the first one by just taking the trace. Now, well, like I said, I made this comment here that this is the adjugate of the matrix A. Also, the adjugate can be computed in a different way, and we will see as we go along. Probably I will be talking about the properties of the adjugate, because we need to know what the adjugate is. It's basically you take the transpose of the complements, right, of the matrix A. And anyway, we will see that. Another consequence, so let's say, I should have said, well, another consequence, but you can write this as so another consequence of Cayley-Hamilton is the following. So if A and M2 of C, I want to see what happens now if the matrix A is non-invertible, is singular, or you can say non-invertible. Well, what I mean by that is that the determinant of A is actually 0, And then something happens with the powers of this. So you can say that a to the power n will be nothing else than just trace of a to the power n minus 1 times a. This is how you can write this for all n in n. Again, this is an easy consequence of the Cayley-Hamilton. You just iterate, right? So you have a squared equals trace of a times a, right? From Cayley-Hamilton, you multiply by a, you keep multiplying, or if you want to prove by induction, step by step. So it follows this. So this is another relation that you should keep in mind. Like I said, you don't have to remember this by heart. For example, another consequence, and I will give this to you as a problem. Let's say, let's do a problem, problem 1. This is a classical problem, which says the following. If A in M2 of C, so I have a 2 by 2 matrix, is nilpotent, whatever that means. So this means that there exists a positive integer k such that a to the power k is O2. Then guess what? A squared is nilpotent, is 0, sorry. And we will prove something even more general. In fact, I think if I look at the schedule, wait a second. I think we're supposed to do only matrices of size 2 today, because I don't want to rush through things. Let me just look. 2 by 2 and 3 by 3. So we have only, we have only 3. Okay. Yeah, we also have to cover 3 by 3 anyway. All right. I want you to think of this problem a bit. And we will prove next week. We will actually prove something more general. So if I have an n by n matrix, which is nilpotent, then a to the power or the size of the matrix will be 0. Anyway, try to prove of this. Think of this problem. So how would you approach such a problem? So let's see. Clearly, if A is nilpotent, so from A to the power k equals 0, it will follow what? By taking the determinant, it follows that what? The determinant of A is 0. That's obvious, right? Is it clear for everybody? Because if you take the determinant, right, in A to the power k equals O2, this will follow that the determinant of A to the k is the 0, but the determinant of A to the k is the determinant of A, everything to the power k. You know that the determinant is multiplicative, so it follows that the determinant is 0. All right. These are basic linear algebra, which are done in a linear algebra course. If you want to remember them, I will invite you to. I have my entire linear algebra course that I taught in the summer. It's on YouTube. It's on my YouTube channel. So you can look there if you want to remember some things. So we know that A is singular. Now from Kaylee Hamilton, what do we have? So we have that A squared, so the determinant 0 is nothing else than just trace of A times A. Well, we have actually the consequence above. And now guess what? We're going to multiply by A over and over again. So now multiply by A. So multiplying by A, we get, let's see, what do we get? So we get A cubed equals trace of A times A squared. But we know that A squared is trace of A times A, which will give us trace of A times trace of A, which is trace of squared of A times A. And by an easy induction, and I'll leave this to you as an exercise, it follows that, in fact, by the above consequence. In fact, I will even said, or by the other consequence, or by the above consequence. It follows that what? That A to the power, well, I wouldn't go to A to the power n, but I will go to the A to the power k is nothing other than just the trace of A, everything to the power k minus 1 times A. But I know that this guy is O2. So we have two cases here. So the first case is when, so case 1, we have trace of A equals 0. And if trace of A equals 0, then we're done. It follows that A to the power, well, if trace of A is 0, then A squared, which is equal to trace of A times A, will be 0 times A, which will be 0, 2. And we're done. And the second case, if A is the null matrix, then it's obvious that A squared is 0, 2. And that's it. That's the solution. Keep this in mind. So that's problem 1 that I have in mind. Now, before I go and talk about some other things, for example, another exercise, and in fact, yeah, why not? So problem 2. In fact, I will tell you this, that this is, you can prove this using eigenvalues, but anyway, we'll go there. So problem 2 says the following. If A is a 2 by 2 matrix, again, with the complex entries, then show that we have that we can express the determinant of A in terms of trace and trace of A squared. So this would be 1 over 2 times the trace of A squared minus trace of A squared. So we have this beautiful formula for the determinant. Like I said, you can use prove this using eigenvalues, but anyway, we don't know that yet. And let's see. Hey, Aaron, did you just wake up?
Yeah, man. Oh no, I didn't just wake up. I just popped in here.
Ah, okay.
Yeah.
All right, let's see this problem. Think of it. Again, the only tool you have at this point is just Kaylee Hamilton. So how would you approach this?
Hey, Cezar, I have a quick question.
Yes.
So is that TR, is that transform of matrix?
No, the trace.
Trace,
Look,
okay.
Look, it's
Sorry, I
defined.
missed that whole first part, yeah.
Yeah. Look here, is defined here. Is the sum of the elements on the main diagonal.
Okay, got you.
And the determinant, well, you know, what the determinant is AD minus BC. So you multiply the elements
Cross
on the
product, and then it's an alternating series of positive and negative values.
Yeah. Okay. And also there is this tool that we said, the Kaylee Hamilton, this guy here. In fact, let me just, this here. This is the Kaylee Hamilton equality, very important equality. Anyway, we will deduce this again once we talk about the characteristic polynomial soon. Anyway, let's see this problem first. I want to play around with some problems without knowing too much. So I want you to see how you can operate with 2x2 matrices. I have some problems here. Anyway. So how would you approach this? So we know from Kaylee Hamilton.
Can we just construct a, say it was a 2x2 matrix?
Yeah.
Can we just construct 4 elements in 2x2 matrix and then?
And yeah, you can actually prove it by computations directly. I agree.
Just substitute in for the trace.
Yeah, exactly. Yeah, you can do that. Or instead of doing all these computations so that I don't lose more time. So from Kaylee Hamilton, but yeah, your approach is good. So from Kaylee Hamilton, we have, let's see, what do we have? So let's write it. So we have that a squared minus trace of a times a plus the determinant of a times the identity is the null matrix, right? So we have this. And now we would like to do something here. So what can we do? What would you do here? Since you're trying to write the determinant, so from here, or we can write this, and let me write it in this way. The determinant of a times the identity is nothing else than just trace of a times a minus a squared. So what would you do here? Let's apply the trace. So applying the trace, taking the trace, what do we get? We get what? We get that, let's write it, so trace of the determinant of a times the identity is the trace of a times a minus a squared. But now by applying the properties of the trace, which I assume you all know them from a linear algebra course, this guy, the determinant is a constant, so this guy here will go outside. So this will be equivalent with the determinant of a times the trace of the identity. And this would be the trace of a times a minus trace of a squared.
Hey, Cezar?
Yes.
So you're just saying one of the properties of trace is a linear operator, so you can like.
Yes, exactly. So it's linear. Yes, exactly. Yeah, exactly. It's a linear operator. So it takes the constant outside, and it's additive. Yeah, exactly. Correct. And now this would be equivalent with what? So again, this would be equivalent with this guy is 2 here, the trace of the identity, so it's 2 times the determinant of A is the same as trace of A times trace of A minus trace of A squared, which is exactly what we want. So equivalent with the determinant of A is 1/2 times trace of A everything squared minus trace of A squared. And that's it. That's the end of it. Keep this relation. Well, I wouldn't say you keep it in mind. You can deduce it. It's anyway. You will see. We go back to this problem once we talk about the eigenvalues. And before I do this, I have one more problem in mind. Let me see. Before I go and talk about other stuff. Anyway, probably. So problem 3. Anyway, let me give you this problem because we will prove this in a more general context. Let AB be 2 by 2 matrices such that the commutator will, this Lie bracket, we will define it in this way. This is what we call the Lie bracket or the additive commutator, which is AB minus BA. This guy is A. Show that A squared is the null matrix. Okay, think about it for a couple of minutes.
Sorry, what was that last part? A squared is equal to what?
A squared is the null matrix, O2.
Null matrix, okay.
So think about it.
So A and B are just any two elements in the 2 by 2 matrix?
Yes. Any two, yes, any two 2 by 2 matrices, yes, correct.
But they don't have to be in a specific order. They can be in any.
Yeah, they don't. You just I'm considering 2 by 2 matrices. Any two, doesn't matter.
Okay.
So you would be thinking of something.
I have a question real quick.
Yes.
What was that thing you said it was called in the brackets?
Lie bracket. Or this is how it's called, the Lie bracket.
Okay, what does that denote? What does that mean? Was the
Well, it's just the additive commutator. It holds more general for any two elements in a.
Oh, additive commutator.
Yes, in a Lie algebra in any way. We can divide the Lie bracket in this way. Or you can say in the case of 2 by 2 or n by n matrices, you define this as the additive commutator. There exists this the so-called multiplicative commutator.
What is the additive commutator representative of, though? Is what I'm trying to ask. Like, it's just a mathematical equation. I mean, what does it represent?
Yeah, well, actually, it comes from physics, I would say. It represents some kind of state in physics and something like this.
can you apply mathematical operations to it though? Can you like square?
Yes, absolutely, absolutely. Yeah. You can iterate it. You can multiply by a. Anyway, there exists the so-called Leibniz rule for this for these commutators, and there is also this so-called the Jacobi identity. It is very important for Lie algebras. When you have you have this, that the bracket, okay, I could say that this holds true. The bracket A, B, C, right? Plus the bracket B, C, A, plus the bracket C, A, B, something like this. This is 0, right? Something like this holds true. Right? Anyway, this is what we call the Jacobi's identity, right? Yeah, and yeah, this is true. This is what we call the Jacobi's identity.
Yeah, so I haven't really gotten far, but my first instinct would be to square the given equation above so that we can.
Yeah, you can do this. Why not, right? But there is something. Well, let me erase this. Well, what can we? First of all, is there a property for the commutator? So this is what we call. Okay, let me say we call this guy AB minus BA the additive commutator of A and B, right? Do you see any property, any immediate property of the commutator? For example, what about the trace? What is the trace of the commutator? Is what? Is? This guy is a trace of AB minus BA. And this is what? Is 0. We know that the trace of AB is the same as trace of BA. So this guy is 0. Okay. So since we know this, it follows that from Kaylee Hamilton identity, what do we have? We have that, well, we apply this for the commutator. So we have that AB bracket squared minus, it will be equal to negative the determinant of AB times the identity. All right. So basically, if we prove that the determinant is 0, then we're done. Because we know that this is actually A squared. So what else can we do? So we have to show that the determinant, so we have to show that the determinant of AB bracket AB is 0. So if we show that, we're done. Correct? Because from Kaylee Hamilton, it will follow that bracket AB squared is 0. So we know that this is 0. So what should we do here? Maybe I should multiply by an A, maybe to see something happens with the trace of AB squared. And maybe, for example, multiply the given identity, the given equality by A, let's say. And what do we have? So we have that, let's see. So we have what? We have that A times bracket AB is the same as so it's A squared, right? A times A, which is A squared. Which will be equal to, if you want, negative determinant of bracket AB times the identity. Right, so in other words, now if we take the trace, so by applying the trace, so that's what we do, we just take the trace. By taking the trace, we have, let's see, that trace of A times A bracket B, which is the same as trace of A squared, basically, is the same as the trace of negative the determinant of bracket AB times the identity. But this guy will be nothing else than just the negative 2 times the determinant. So by applying the linearity of trace, the determinant of bracket AB. So in other words, proving that this guy is 0 is equivalent with proving that trace of A squared is 0. So why is this trace of A squared is 0? Right, you see, this guy and this guy are the same. But now the key fact is here, right here, but we haven't seen it. Let's look at this. Let's compute it. But let's use actually the definition. So we have that by the definition that trace of A bracket AB, and let's see who this guy really is. And this is the trace of A times AB minus BA. And let's multiply here. And this will be nothing other than just the trace of A squared B minus ABA. Which, if you want to put it this way, let me write it in this way. So it's trace of AAB minus, okay, minus trace of ABA. But this will be equal to what? Can you tell me? What is this equal to? Keep in mind that we have this property of the trace.
It's 0 by the Hamilton.
Exactly. The trace of xy is the same as yx, and you can take here x to be what? You can take x to be a and y to be ab. So you can just put it right. Take x to be a and y to be ab. And this guy will give you 0. And now, since this guy is 0, it will follow that the determinant is 0. So the determinant of the bracket AB is 0. And finally, this will imply that A squared is 0 by Kaylee Hamilton. And that's the problem. Well, probably you could have solved it simpler than this, easier. Yeah, I think I have it somewhere in my notes in just a few lines, but I wanted to explain conceptually what's going on here. So basically, you just use it, the Cayley-Hamilton and the properties of the trace. All right, now, whoa, I want to veer towards something. And in fact, I would like to talk about the characteristic polynomial. Of A. What is this characteristic polynomial? Well, the characteristic polynomial of the matrix A, so keep in mind that we are 2 by 2, is given by the following. Is P, okay, let me write like this. So this guy is P sub A of lambda is the determinant of lambda times the identity minus A. And this guy, if you expand this guy, if you write it in this way, and I leave it to you as an exercise, is lambda squared minus, and I'll have these coefficients here, trace of A times lambda, oops, sorry, times lambda, plus the determinant of A. That is a characteristic polynomial. Of the matrix A. So it's given by this, right? And also Cayley-Hamilton can be written as, for lambda equals matrix A, you can take the matrix A, we obtain that PA of A is the null matrix. So it's nothing else than just Cayley-Hamilton. So if you take, it's A squared minus trace of A times A plus the determinant of A times the identity, well, is the null matrix. Well, I could have started just like this, but I wanted to play around with that. So this is what the Cayley-Hamilton, it's obtained immediately. Okay, right? So this is the story for 2 by 2 matrices. And in fact, we can even write even more general. Well, it doesn't matter the way you write it. So you can write, we can write this in the following way. So we can write PA of lambda, the characteristic polynomial, also as the determinant of A minus lambda times the identity, because it's just a -1 to the power, -1 squared, which is 1. So it doesn't really matter. For 3 by 3, we'll have a negative there. But anyway, you will see. Now, this is as you can see here, let me point out the remark. So the zeros of the equation, of the characteristic equation, of the characteristic equation. And when I say by the characteristic equation, I mean this, okay? PA of lambda equals 0, right? Are called the eigenvalues of the matrix A. All right, so now since we have 2 eigenvalues, right? Since we have it's a quadratic polynomial, right? We have 2 eigenvalues. So lambda 1 and lambda 2. And moreover, they satisfy the following. Moreover, they satisfy the following relations. And let's see what kind of relations do they satisfy. And they satisfy the following relations. Let me write them like this. So it's lambda 1 plus lambda 2 equals the trace of A, right, from Viet relations. And lambda 1 times lambda 2 is the determinant of A. This is what they satisfy, right? Keep that in mind. Of course, now if you want to go back to problem 2, it will follow immediately, so there is no problem with that. So this is the characteristic polynomial of this. And in fact, if we want to go back to problem 2, where is it? Problem 2 follows immediately from this. So problem 2, and I'll leave this to you as an exercise. So problem 2 follows immediately from, well, let's call these something, this 1 from 1. Well, let me remind you that problem 2 stated that the determinant of A is 1/2 times the trace of A, everything squared, minus trace of A squared. Well, how does it follow? Well, the eigenvalues of A squared, so if I like to say one thing, but this is more like a disguise from the spectral theorem, which I would like to mention. So if the lambda 1 and lambda 2 are the eigenvalues of the matrix A, then lambda 1 squared and lambda 2 squared are the eigenvalues of A squared. So now this equality, so the above equality is equivalent with, so well, reduces to, well, lambda, we know that the determinant is the product of the eigenvalues, which is 1/2 times lambda 1 plus lambda 2 squared, everything squared, minus lambda 1 squared plus lambda 2 squared. Well, I think you can check this identity. It's pretty trivial. It's just a basic algebra, basic college algebra. And I told you at the beginning of the first lecture that when we did those identities and inequalities, that they will come into play. They will be very relevant for when we talk about matrices over sizes 2 and 3. All right, now I will call, now what if I want to generalize things a bit? And what if I want to, well, I'll call this so-called let's say a more general, and I'll put it like this, in quotes, a more general formula for the, let's say, for the characteristic polynomial. And again, I'll call characteristic, again, I'll put it like this, polynomial, because it's not quite a characteristic polynomial of two matrices. And I'll explain immediately what do I mean by that. And you'll see how useful this will be in applications. For example, we have the following. I'm going to denote it in this way. In fact, so P of A, B of lambda, which I'll denote it in this way, is A plus lambda B. I have two matrices here, A and B, 2 by 2 matrices. And this would be equal to, and hold your breath here, I'll have this coefficient in the determinant of B times lambda squared. And I'll have the, this coefficient here, plus, and I'll write this coefficient the following way. This would be the trace of A times the trace of B. Anyway, it doesn't really matter that much, times the minus trace of AB times lambda, plus the free coefficient, which will be the term of A. So this is how we can write this. And of course, if you take B to be the identity, well, I hope you can see this here. Right? Is it clear? You can see the coefficient. So this guy here is the trace of AB. So if you take B to be lambda, and if you put this with the negative, if you want, you'll get exactly the the formula for the characteristic polynomial, right? But yes, you'll get exactly the formula for the characteristic polynomial. So take B, so take B to be the identity, and we get the characteristic polynomial. Well, you have to change the signs there, like characteristic polynomial. Okay. Now, well, I'm not going to get into the proof of this, but the proof uses this identity here. Surprisingly, huh? This problem. And I'll leave it to you as an exercise. Instead of A, you just take A plus lambda B, and you just apply it, and you will see you'll get exactly this. Anyway, I'll leave this to you as an exercise. Now, as a immediate corollary, so, and I will leave this to you as a problem. In fact, I will do it as a problem, problem 3, which is a very important identity. Very important identity. Probably I think I'm going to do a separate video for 3x3 matrices, because I don't think I will have time for now, since there are some problems that I would like to cover. So this identity says the following: if A and B are 2x2 matrices, then we have, and I'm going to write it like this, the determinant of A plus B plus the determinant of A minus B is 2 times the determinant of A plus the determinant of B. So let's think of this. All right, let's see. Okay, I'm going to leave it like this so that you can see the hint.
Are we supposed to show what's in red? Is that what we're supposed to do?
Yeah.
Okay.
Show this. So think about this a bit. I think you have the all the information you have. It's above. Just look at that characteristic polynomial, whatever.
you substitute the trace as the, because this isn't like the cross product or like the determinant, essentially it's the cross product.
Even simpler than this. Just look at the, so we know that PAB of lambda is the determinant of A plus lambda B. And look what you have to prove. Maybe there is some particular value of that polynomial.
Okay, so but the above expression has a like a constant lambda in front of B though, right?
Yes, but look at it. So that, can you express determinant of A plus B in terms of that polynomial that you see above?
Yeah, so could you just set lambda equal to 1?
Exactly. So one of them is P of 1, and the other one is what? What is determinant of A plus B? Look at the formula here. So determinant of A plus B is P of 1. P of 1 is determinant of, okay, let me write like this. So we have that the determinant of A plus B is P of 1, right? But this guy P of 1 is also what? Is, if we look at the identity, is what? Is the determinant of B plus this guy trace of A, trace of B, minus trace of AB times 1 plus determinant of A, right? And the same thing goes for determinant of A minus B is P of -1. So we just take lambda to be -1, which is, let's say it will be the determinant of B, because -1 squared is 1. And this guy here, it will be negative. So it will be negative trace of A, trace of B, minus trace of AB, plus the determinant of A. So now what are we going to do? We're just going to add these two. Let's say this is star and 2 star. So add up star and 2 star, and we get
the determinant of B plus determinant of A.
Look, you have them twice here, see?
Oh, okay, yeah. So,
but this guy will vanish because you have a negative and a plus. So we have that, which is nothing else than just determinant of A plus B plus the determinant of A minus B is the same as 2 times the determinant of A plus the determinant of B. Keep in mind this identity, it's a very important one, and you will see in applications. So always this holds true. For example, well, I want to say, let's use this identity, but let me give you, in fact, I'll give you some problems. In fact, I'll do a couple of them. Ooh, okay, so I haven't planned to do some. For example, let's say problem 4. Which says the following. Let AB be 2 matrices, 2 by 2 matrices. Show that if, in fact, show that okay, now let me put it like this, such that AB is the same as BA. Show that, so they commute, so show that the determinant of A squared plus B squared is greater or equal than the determinant of A minus the determinant of B, everything squared. All right. And you see we have this equality here. Well, of course, this will be, there is a classic problem which says that if I have two matrices, and this holds true for n by n matrices, which says that, and probably we'll discuss this when we'll talk about next week. If I have two matrices, so n by n this time, such that they commute, then the determinant of a squared plus b squared is always non-negative. But this, for n equals 2, you can actually prove something stronger than this. Well, of course, that is non-negative. That's obvious. So how should we prove this? So maybe we could use our identity. So let's using the above identity. And let me write it again. The determinant of x plus y plus the determinant of x minus y is 2 times the determinant of x plus the determinant of y. So using this identity, right? And I'm going to take for some particular matrices, for x to be, let's say, x squared plus b squared, and y, this will be a b plus ba. And let's see, what do we get? We obtain, let's see, what do we obtain? So we obtain that the determinant of a squared plus b squared plus ab plus ba. You'll see why I did this. Maybe this will ring a bell. Plus the determinant of a squared plus b squared minus ab minus ba. Maybe you'll tell me who this is. But anyway, you already know that these guys commute, but anyway, you can write them. Is the same as 2 times the determinant of a squared plus b squared plus the determinant of ab plus ba. Anyway, also keep in mind that, so we know that that who is this guy? That a squared plus b squared plus ab plus ba. Who is this guy? Can you tell me? Does this ring a bell? This is nothing else, it's just a plus b, everything squared. And a squared plus b squared minus ab minus ba is nothing else than just a minus b, everything squared. So everything will boil down to, so finally, we will have that what? That the determinant, let me write it in this way, that a plus b squared, okay, I can write like this, plus the determinant of a minus b squared is nothing else than just 2 times the determinant of a squared plus b squared plus, okay, let me write it, the determinant of a b plus ba. So we have this in general, this identity. This is what we obtained. So this holds true for any 2 by 2 matrices from the previous identity. And now let's look at our problem. So I know that AB equals BA. So this will be, this is equivalent with what? With the determinant of a plus b squared plus the determinant of a minus b squared is 2 times the determinant of a squared plus b squared plus this is equal, it's what is this? The determinant of, well, 2ab, if you want to put it like this, right? Okay, but now let's treat this, look at these guys here. So this is, let's say it's like an alpha, and this is like a beta. So by the elementary inequality, alpha squared plus beta squared greater or equal than alpha plus beta everything squared over 2. So by this elementary inequality, guess what we have? So we obtain that this guy here, the determinant of a plus b squared, which is the determinant of a plus b everything squared plus the determinant, let me write it in this way, a minus b squared is greater or equal than the determinant of a plus b plus the determinant of a minus b everything squared over 2. But this guy here, this will be equal to 2 times the determinant of a plus the determinant of b sorry, 2 squared here, right? Oh, in fact, I can say 2, and that's it, right? Anyway, and now you can play around with these. The 2 will go away, and you'll derive the conclusion. And now, anyway, I'll leave it to you. So I'll leave it to you to finish off the problem, because I would like to cover another one. So, and finish off the problem. I think you can do it from here. Finish off the problem. All right, you can do it from here, I'm pretty sure. It was tricky, I would say. And now problem 5, I want to give, this is a Putnam problem. I think it was a Putnam A4 or A5, I don't recall exactly, in 1994. Definitely wasn't one of the easy Putnam problems. So the problem states the following: let AB be two by two matrices with integer entries, such that the following property holds true, such that A plus B, A plus 2B, A plus 3B, and even A plus 4B. So these matrices, these 5 matrices, are invertible. And moreover, their inverses are in M2 of Z, so have entries, integer entries as well. No, this is a very piece of information here. Then the problem asks us to show that this matrix A plus 5B is also invertible, and the inverse of this matrix will have integer entries as well. All right, I want you to look at this problem.
Cezar?
Yes.
A quick comment question. If a matrix is invertible, that means its determinant is 0, right?
Non-zero.
Non-zero.
Here you have to point, we have to point out a small thing, but maybe we'll realize this. What happens? So look, matrix invertible and their inverses are in M2 of Z. So this should immediately pop out something inside you, like, should ring a bell, like something happens. So when a matrix with integer entries is inverse, and moreover, the inverse is also with integer entries, so something happens. So that's the first observation you need to make.
Don't these all have determinant 1?
Even better than that? Well, almost, plus minus 1, right? So let's point out this crucial fact. And I'll leave this to you as an exercise to prove it, because it's quite easy to well, in fact, I wanted to put this fact as an exam, a hard exam problem in my linear algebra, but anyway, maybe I should do it next time when I will teach linear algebra. Because it's very important to have these small problems so that you can learn something from them. So the fact is the following. So if we have a matrix C and M2 of Z, right, then the inverse is in M2 of Z if and only if the determinant of C is plus minus 1. So this is the fact. Very important fact. Now let's use this fact. So what do we know? Let's, based on everything we said here, let's define, so define the polynomial PAB of lambda is the determinant of A plus lambda B. What do we know about this polynomial? We can actually write it, right? You see, we can actually write it. Where is it? Look at it. Wow. We actually know who this guy is. So let's rewrite it again. So we have an explicit form of this guy. So this is the determinant of B times lambda squared plus, this guy was here, plus the trace of A times trace of B minus trace of AB times lambda plus the determinant of A. Can you tell me what is the degree of this? It's at most 2, so right, the degree of this polynomial is 2, or at most 2, let's say. Okay, and let's see, what do we know so far? We know that PAB of what values? Of 0, of 1, of 2, of 3, of 4. Ouch. Oh my. So I know that this is, these values are what? Belong to what set based on the fact?
They're in Z, right?
Pay attention. Based on this fact, because and what the problem asks us, I know that these 5 values belong to this set, plus minus 1.
Plus or minus 1, right? Yeah. So, but isn't it constrained to like only whole integers though?
Yeah, but yeah, they're integers. You see, look at the problem statement. They're invertible. These values, P of 0, P of 1, P of 2, P of 3, P of 4 are invertible, and moreover, their inverse is in M2 of Z. So
because you use the identity, it says that they have to be an element in plus or minus 1 if it's
exactly. So I use the fact. And I know that these 5 values belong to this set. So what can you tell me about this pigeonhole principle? If you apply the pigeonhole principle, I have 5 values belong to the set in the set of only 2 elements. So what can you tell me by the pigeonhole principle? that at least 3 of them will be equal, right?
Yeah, either 3 of them will be positive or negative.
Exactly, will be equal, both of them, plus or
Yeah,
minus
same
1.
integer.
Exactly, so by the pigeonhole principle, this is a very nice problem. How should I say it? At least three of them, of the above values, so at least three out of this 5 will have the same value. So in other words, this means that P of A, B of, let's say it doesn't matter, I is the same as P of A, B of J is the same of, with P of A, B of K. And moreover, these are plus minus 1. So either way. In fact, let me write like this. Why should I? It equals plus minus 1. Okay, but the degree is 2, is at most 2, but the degree of my polynomial is at most 2. So what can you tell me? Again, by the pigeonhole principle, it follows that. So I have the degree at most 2, but for 3 values, it's 1. So it follows that it is that constant. So it follows that P of A, B is actually constant. And not just a constant, when I say constant, it's either 1 or negative 1. That's what I mean by that constant, right?
Yeah.
So, and therefore, in particular, if you plug in 5, in particular, PA of B of 5 is constant. And which is either 1 or negative 1. So by the lemma, because by this fact, because it's if and only if, it will imply that by the fact, this implies that this guy is invertible, right? So that A plus 5B is invertible. And moreover, A plus the inverse of this guy is in M2 of Z. And that's it. Very beautiful problem. In fact, one can prove it, maybe you will prove it, that if I drop one condition here, for example, if I drop that, the last one, A plus 4B, so I have only 4 of them, only 4 of them to be invertible, the problem doesn't hold true anymore. Anyway, I think I'm going to stop here. Thank you very much. In fact, I have a question. Was this last problem clear? Jack, was it clear?
Yeah.
All right, that's good. Very beautiful problem, I would say. Okay, guys, I think I'm going to stop. I hope you enjoyed this. Unfortunately, I didn't have time to talk about the matrices of size 3. I will do it. And I had one more problem to do, but probably I'll use this problem for the recitation because there are 2 approaches to this problem. It's a very beautiful problem as well. It's from some old Romanian Olympiad. Anyway, I'll stop here. Thank you very much.